So we have
Okay, but it will just
16 45 minutes. Okay, so this session, we decided this is very free-form among the three of us. We're simply going to talk to you a little bit about some ideas that we have on where the future might be going. Each of us has 15 minutes, and it's very important, Kathy, that you and I keep the 15 minutes because if Neil runs out of time, he can't go home. Right? If he doesn't talk to us about JWST, NASA will not permit him to come home.
Fortunately, I don't work for NASA, so that's good.
You don't work for NASA? Okay, well, in that case.
But we already signed the petition.
You go as long as you want, Kathy. All right. So tell me, if you would, give me 5 minutes in 10 minutes. So, to my mind, one of the most interesting things that I thought actually coming into this meeting, and now I think it's even more interesting, is this question of how are we going to determine where the location of the gas is in the embedded clusters. To a large extent, embedded simply means that we can't see them ocularly. Well, that's fine, but of course, if you have a grouping of stars here, the gas can be here, or the gas can be here. And even in the case of the Orion Nebula, where we do see the stars, we really are very uncertain about whether the gas is here or actually way back here. And that's just central to the entire dynamical picture that we've been talking about throughout. And now it's even more intriguing, given the result that we've heard several times, is that possibly, based on the simulations, the gas may not even be coexistent with the clusters. I think that's really interesting. I think it's really uncertain, but I think it's really interesting. And I put this one up first because I think it's one of the most important, and I have the least idea how to do it, which is why the question mark is actually the first bullet. I mean, clearly, and it's interesting, something that has been mentioned much in this school is ALMA, which is coming online, which, just like Gaia, is going to absolutely revolutionize our understanding of disks, of gas locations at very, very high resolution scales. Whether, in fact, we can use ALMA to get any sense of location with respect to the stars is not clear to me at all. I could imagine that if you can get down to an adequately clumpy, in other words, a high resolution image of an embedded cluster, that if the gas is closely associated, I could imagine that you might see some correlation between either at least the clumpiness of the stars and the gas, maybe even some association between the stars and the gas, some correlation between the two. But you know, you've got to be way less than a dynamical crossing time for that to hold true. But nonetheless, I'm really sort of grasping at straws here, and I look forward to the conversation this evening about how the images of the gas might help us with this question. Possibly we'll be able to see some structure in the extinction. If again, the gas is closely associated with the stars, and we're looking at extinction from the stars, maybe we might be able to, we'd have to do it in the infrared, get some extinction measures. I was intrigued by Kathy's thought about infrared excesses. But more broadly, it's something I really hadn't thought about, is signatures of the impact of the stars on the gas. In other words, if they're coexisting, then it's quite possible that the stars will literally affect what we see from the gas in some sort of additive way. And that's an idea that I was intrigued by when it was mentioned, and I haven't thought enough about. But I think broadly speaking, I think this is one of the major questions in the field. And observationally, I'm not entirely sure how to get at it. I lay it out there. The internal kinematics, of course, we came in knowing that we would need to do. I think at the end of the lecture I gave yesterday morning, you at least got a sense of how large scale, by large scale I don't mean scale on the sky, I mean large scale in terms of numbers of stars, numbers of observations. High precision optical radial velocity surveys have, I think, may have the opportunity to get at systemic motions. Kathy's concern is well taken about expansion and contraction to radial velocities look very similar. So there will be issues there, but nonetheless, this is something that we can do right now, and I suspect is being done right now. Although interestingly, I believe the hectashell is being taken off the MMT. So that particular initiative may have to shift to the south. And northern regions may be a little bit shortchanged on this. Obviously, Gaia is going to be the game changer in this one. I mean, Gaia will be able to give us the two-dimensional motions in the sky with very high precision, and there's no ambiguity in proper motions about expansion or contraction. So, but it is optical. I mean, it's not a very big but, it's going to be wonderful. But it is optical, and so that means that Gaia is not going to get us to the very youngest systems. And I think we need to start thinking about how we're going to get infrared proper motions and radial velocities at less than 1 kilometer per second precision. This is already happening. I mean, in the infrared, it's not tremendously difficult to get there. I don't know of 300 fiber, 300 object infrared spectrographs yet. Perhaps some of you do at high resolution. But it's going to come. I mean, this is going to follow the optical without a doubt. And so we should actually be able to get into the embedded regions. Infrared proper motions, Miriam and I have been talking, well, she's been telling me about the possibilities. I actually don't know much about this, but in principle, there's no reason why we can't do this, other than perhaps just lifetimes. The young binary populations, I mean, this is still a wide open world. So these issues are more with respect to not how they form, which is what I was talking about yesterday, and how they evolve, but rather to the regions themselves. So the same large-scale high-precision optical radial velocity surveys, or infrared for that matter, can't avoid detecting spectroscopic binaries. And if there's anything that has made my career, it is that people have a tendency, especially PhD students, to get those data, publish them, say these are binaries, and then go on and do something else. And I guess it's just sort of my slightly Swiss nature that I'm willing to work on these for 10 years and get sequential observations. So we're talking about monitoring here. But the beauty of this, and this is something that imaging will never provide at a large separation, is that you get the orbital parameters. And so there's a lot of information. As Kathy was saying, maybe the simulations aren't there yet in their accuracy, but they will be. And there's a tremendous amount of information in the orbital eccentricities and the period distributions, all around this issue that has come up so many times at this meeting of binary processing. And I will say on the theoretical side, the level that I'm hearing that this is happening suggests that there needs to be a lot of theoretical work pursued on this to make sure that we have good theory to compare to this and to make sure that the processing actually happens. So this can be done right now. It just takes a bit of patience and perhaps tenure. This is something that I know is going on in Grenoble and France, and I think broadly speaking is going to be coming, which is high-resolution surveys of protostars. Obviously, this is fascinating from the point of view of the formation of the binaries, but it too is relevant to the binary processing. Right? I mean, we need to understand, if we're going to think binary processing within 1 million years is relevant, then we're going to have some hint of what the actual formation distributions are in order to compare the million-year systems to the 10 to the 50-year systems. This is happening right now, and I'm sure that this is going to come out and accelerate during the decade. I'll just point out that the interferometers now, the optical and infrared interferometers, it's a wonderful time to be alive if you enjoy stellar masses, because they're starting to get together. And when you have an interferometer and radial velocities, you get out masses. In fact, arguably, you get out the best masses that are possible, except perhaps for eclipsing binaries. And that hopefully will lead to accurate stellar evolution tracks, which hopefully will lead back to all these mass spectra that we've been looking at, all these IMFs. We've seen a lot of IMFs during this school. And this really should fundamentally tie them down in terms of their masses. Then Kathy's brought up this interesting thought about wide binaries. I've been intrigued about soft binaries since I was a kid, only because the dynamicists, ever since Douglas Hege wrote his paper, told us they should be in an equilibrium distribution in clusters. It's a very definite prediction that they should, in a sense, they should be far deficient compared to the field. But ironically, even though they're very easy to see, it's not a technical problem, it's a purely statistical problem of determining which of those pairs of stars in a cluster are actually wide binaries. I think it's a quite tractable problem, and if the theorists can give us more motivation for why we should go after this, I think it's there to be had right now. The young massive clusters we haven't talked about a whole lot. My guess is that there's a lot to be learned from them, and the high resolution imaging that's still possible from the ground right now will ultimately, and JWST is going to kill this field. It's going to be wonderful, but I wouldn't wait. We have an election coming up in the U.S., and anything could happen. So I really think we need to be pushing on this now. Unfortunately, a lot of people are because of the relationship to extragalactic clusters. It's one of the best links. And again, on these, if we could get, and here we don't need proper motions and radial velocities at quite the same precision as I was saying before. These are massive, they're more globular cluster-like at similar densities, so the internal motions aren't as high. Are higher. And so you don't need as precise proper motions and radial velocities to get into their dynamics. So this can be done behind adaptive optics. To say, the problem, of course, is crowding. The problem is getting into them. I know that Michael and his collaborators have a nice piece of work on Westerland 1. I think we're going to continue that on many fields. So I think we're going to learn things here. I'm not entirely sure what they're going to be.
5.
5? Okay, great. Perfect. So finally, disk frequencies. There's been a lot of work on disk frequencies because most people are looking at it in the context of the evolution of disks, because with respect to planetary formation. It's really critical to get sort of a natural evolutionary time, and in particular when the dust forms into larger physical bodies that then form into planetesimas that form into planets. So disk frequency to a large extent has been studied in that context. There's actually a lot of data out there right now. But it also, I believe, can be a key tracer for the early dynamics of these systems through the truncation that we were talking about before. It's a little tricky. It's subtle in that most of the studies on disks so far have been at near-infrared wavelengths, maybe mid-infrared wavelengths. So you're talking about regions of the disk from sort of, really a few tenths of a stellar radii out to a few AU. So most of the surveys so far have been in the context of the inner disks, which is quite adequate for planet formation. But if you really want to find out whether there's truncation or not, we're going to have to start looking at the outer disks. And so we're really talking about long wavelength surveys here, sort of at the 100 micron kind of level, or perhaps masses. If we see some evidence of a drop in masses, we might be able to get a truncation from that. And ALMA is certainly going to help us there. In fact, ALMA is going to resolve these disks. So I now actually realize, even as I wrote that, I was being an old fogey. Because I was actually thinking about sensitivity on sub-millimeter detections of masses. But ALMA, with any luck, will actually resolve these disks, and we may actually be able to see evidence for truncation in these systems. But remember, there are other things that can truncate, and if you remember nothing else from me except for G equals 1 over 233, and half the stars are binaries. Don't ever forget that, because they will impact on every interpretation that you need to make. They will either add uncertainty or they will add incredible insight. I prefer to think incredible insight. So in any case, the high resolution radii that we're talking about here on the disks from ALMA and also in the infrared may give us a sense of the dynamics and the evolution of the dynamics. And then I have to say this simply because otherwise I wouldn't get funding. But I'm only half joking. I think it's going to be very interesting as we start being able to look for evidence for planets in these systems. Planets are, in a sense, a proxy for these same issues, just as Neil was telling us this morning. This is a ways downstream of the regions we're talking about. Certainly people are already looking for planets in open clusters. I mean, that's being done right now. Looking for planets in younger systems, which is to say trying to get to, if you're doing it through radial velocities, 1 meter per second precision on pre-main sequence stars. That's a bit of a fundamental trick. But I have no doubt that we're going to start getting into disk-bearing systems with planets. And when we do, that will give us similar information on the dynamical evolution as we look at the more distributed, lower density population and the higher density population. So I think it's a very rich world to go. This is by no means comprehensive. I will tell you that of them all, the one that I'm leaving this meeting most intrigued about is this one, but it's also the one that I least know how to do. So on that note, Kathy.
So while I'm just setting up here, actually, when I gave my lecture yesterday, I thought I'd finished. I'd actually forgotten that I had to do anything today. No, I don't have anything more to say. And I don't really want to spend 15 minutes on the future. I'll spend a couple of slides on the future. Yeah, microphone. So what happened then was that I foolishly asked Mike for more homework in terms of what I should do, and he said, well, nobody has touched on this really interesting issue about the relative kinematics of dust and, of gas and stars in star-forming regions. I'm going to get out of this now. Hit the text, please. So I'm actually going to just talk a little bit more than I discovered from literature last night, just to share with you. But I'll start with these sort of more global overview stuff. I think what needs to be done in simulations is pretty obvious to most people. I mean, you have to put in all the physics. And in answer to Richard's question, no, I don't think there's anything major that isn't in there. The problem is that it's in there piecemeal right now. I don't know whether it's the right way to go to do what the Amuse collaboration is doing. This is Simon Portuguese-Spartan collaborators who are bolting together all these disparate codes with a sort of script that allow them to talk to one another. It's an intriguing idea. It could be very fruitful. I'm not a programmer. I don't know. I know in practice when you combine various physical effects that you should never be more accurate than the least accurate component of your ensemble, and therefore it may not be the most efficient thing to do to just bolt together all the things which have been optimised for their bit of the problem. But I really don't know, so I just think this is an emerging field. If you're interested in those kinds of things, you should email Simon Portuguese-Spartan. You can go to Amuse meetings where people discuss how they're going on this big enterprise. Converged simulations would be nice, converged in terms of numerical resolution. And I don't mean that convergence means that you produce a star in exactly the same place at exactly the same time, because there's an element of the weather in random seeds, but you want them to be converged in terms of statistical outcome. So yes, you want good statistics. I've already said the more physics you put in, the smaller your simulation has to be, and therefore you don't get statistics at the moment. But Michael said to me, what's going to happen, what do we want in a decade's time? And I think it's the combination of the physics and the statistics to be compared with observations. And something we haven't talked about much here is that you want good post-processing tools when you've done your simulations so you can compare with observations. And in particular with Herschel and ALMA, lots of gas phase diagnostics from which we get the kinematics, you want to be able to make synthetic maps of your simulations. And unfortunately, that means chemistry. It's not just like dust, where you tot up column densities and calculate temperatures. It gets a lot more complicated if you want to know which part of your column that you're looking at is actually contributing most of the emission and therefore the kinematic information. There's lovely work going on in Heidelberg, Simon Glover and collaborators putting atomic and chemical molecular chemistry modules into these post-processing packages, so that, I think in the next few years, when you've done your simulation, obviously not putting in chemistry in a dynamical simulation generally, but you can go back and study the kinematics. And of course, kinematics in the gas is what I'm going to be talking about in just a second. But perhaps most crucially, going back to my first lecture, you really want to get away from the idea of an isolated system in a box, or if it's an SDH simulation, just an isolated system, and which we let go, and which we don't allow to interact with the surrounding environment, because those people who approach the problem the other way and do galactic scale simulations, they actually find that the entities that they create in these simulations are being buffeted by one another on the kinds of timescales that we're considering when we're forming star formation inside there. But the galactic scale simulations at the moment can just about resolve with a few resolution elements the clouds that they create. And so they can do a bit on trying to reproduce Larson's first law, that's velocity width against size. They can do a bit on angular momentum. And they can get a few global properties of the clouds, but they're not really telling you much anything at all about star formation inside. That's all done by prescription, subgrid physics, if you want to use a phrase from cosmological simulations. So, again, a wish list for 10 years or 20 years is to be able to...
Can I maybe make a comment there?
Yeah.
So there's people that do these sort of Zoom simulations,
Yeah.
where they run large-scale simulations,
Yeah.
and then just sort of rewind them and look at a part, and then they do these
Yeah.
in high resolution.
Yeah,
It sort of gives you the boundary conditions implicitly.
Yep.
It's great.
That's exactly the sort of thing which people like Claire Dobbs
Right.
are gearing up to, or in the process of doing right now, I think. And just to make a caution that if we want to understand the Earth's atmosphere, we don't take a picture of the clouds out on the mountain out there and say, I'm going to produce a simulation which is going to recreate that shape, okay? We're not doing weather forecasting. We want to not create individual objects with exquisite accuracy and wondering exactly where each star and where each piece of gas came from. We want to be broadly happy that we've put the right physics in and that it's creating something which is statistically equivalent to what we see. And so to answer the question, what is statistically equivalent, you have to develop the methods to make quantitative comparisons. And actually, I think that's an area where we're doing quite well. I think a lot of work's been done in the last few years, which will be very fruitfully applied to comparing observations and simulations. Things on mass segregation that I talked about, and minimum spanning trees, etc. There probably is still more work to be done, but I think people are definitely thinking that way. And the caveat at the bottom is it's very tempting if you've got a computer and lots of time, and you can do a simulation with 1 million objects, whatever, say, oh good, I can model 30 Dorads or whatever. But never run a simulation without at least one precise question in your mind when you're doing it, because that's what we do the simulations for, to ask, to answer some question. Of course, other things may pop out of the simulations as you go, but try and be focused on an overarching question. Now, this is the homework set. What's the information that we get from the observed kinematics of the gas and either the stars or the pre-stellar cores, I'll define in a moment, in star-forming regions. So the pre-stellar cores, they're dense concentrations, often detected in dust and various molecules. They are often gravitationally bound, and their free-fall times are of order 10 to 5 years or so. So they haven't formed a star yet. They don't have infrared luminosity sources in the centre, so stars or pre-stellar, but they're probably already quite well-defined gravitational entities, or at least some of them are. You can argue as to whether some of them are still fluff, but they're probably in some ways equivalent to the sync particles that pop out of the numerical simulations. And so the question you want to ask is, in the observations, you get information not only now about the kinematics of these cores, but also about the kinematics of the fluff, if you like, the lower density material probed in 13CO, which is along the line of sight. And so you can start looking at differential velocities between the cores and the gas from which it forms, and ask the question, how do the observations, how the simulations do in matching observations? And in terms of probing gas down on the scale of where the stars are or where the cores are, following on Bob's point, that we want to know, is there diffuse gas in among the cores? Well, people have never done the analyses asking that precise question, but there's no doubt that they're looking at gas in the vicinity of their protoclusters and modelling its kinematics, particularly using CS line profiles. And it would be very interesting to know, ask the pundits in that area, whether there are kinematic distinctions between the embedded cluster. You're the observers, here's the cluster, is the gas inside here, or is it just out here and in falling? Could you distinguish that? So that's another thought. But Oh yes, well, why don't I like core mass functions? The reason is this, I'm not saying for a moment that I don't think cores exist or they're not interesting entities, but this plot really made me suspicious. So this is coming out of Herschel data recently, and it's doing a probability density function, a mass spectrum, a core mass function in two different regions, Kilo and Polaris. And the thing that really sort of screamed out of me from this plot is that the core mass function, which the blue curves in this point, both lie with a peak exactly the same relationship to the incompleteness threshold in both cases. This isn't commented on in the paper, and I really think it's something that needs to be addressed, because a lot of mileage is got from saying there's a physical significance to this peak and comparing it with the initial mass function. These are all interesting questions, but you know, I really worry about this. That's somewhat of an aside, because whether or not you think the core mass function exists, you can still use these cores as kinematic tracers and answer some of the questions that I'm coming on to. And so, yeah. Well, I've only got 5 minutes, so I guess I should go. This afternoon. So, over the years, Philippe André and his group have done lovely work in a number of star-forming regions, looking at the kinematics and identifying the cores. So this is rho Ophiuchus. These are the cores, these objects colour-coded according to their velocities along the line of sight, as measured in N2H plus. And over the years, I've often met Philippe at conferences, and he said, kind of dynamical models that Bate and Bernal do don't work because you have your stars whizzing around, and my stars are basically virtually stationary. Their velocity dispersion is roughly thermal. They don't have any time to move anywhere in their natal environments. So all these dynamic interactions that you talk about really aren't happening because they're kind of pinned in place. Now, again, Michael and I were discussing that seems an intriguing result, because once something is actually sort of fragmented out, it shouldn't be held in place. It should actually move in its local potential. So if these things really are very stationary, then that's very, very interesting. And it's stupid to me that over the years, although Philippe has said this to me a number of times, I've never actually gone away and looked at the paper and seen what it said. So here are the various, I regard these as little clusters in here, in the fragmented region of rho Ophiuchus. You can see the scale here. And the sort of story out there, the small relative velocity dispersion implies the condensations, of course, and don't have time to interact with one another before evolving into purely sequence objects. Because remember, they've got their own internal collapse time of about 10 to the 5 years. So, as I say, the simulations would expect these to be not whizzing around, but moving in gravitational potential down there. And the sort of message that I've been picking up and said here is that actually they're not doing that. So, as I say, the first time, like last night, I decided to upload it, and it's really interesting. So, 1D velocity dispersion to cores is 0.4 kilometers a second, which is about twice sonic. And so the 3D velocity dispersion is about 0.6, 0.7 kilometers a second. So, but they're moving supersonically. This is with respect to each other within one of these little cores. And if you look at the size of this little, not little cluster, if you look at the size of this little cluster up here and divide it by this, then the crossing time in there is 10 to the 5 years. Okay, so they are able, on their own internal collapse times, to move around in there. But how does that compare with the free fall time in here? In other words, is this just gravitational motions, which is what I'd expect? So it's a bit difficult to figure out what the total mass is in here from the paper, but I think that the total mass is not more than a factor 2 or more greater than the actual mass of the cores. So I was able to do that little calculation of the free fall time here, and it's also about 10 to the 5 years. So I think, and it's a great shame that Philippe isn't in the room to put the other case, to my mind, but of course I could say this, wouldn't I? This really does look like a little cluster doing what you'd expect it to do, with the stars moving gravitationally in the potential down there. This isn't the question that Bob raised, the subtler questions to whether the gas is down there, in there, that you certainly can't pull that question out of the paper, but you can say that given the kind of total mass you think is there, these have got gravitational motions. And then moreover, if you look at the kinematic differences across this whole region, so this is across a parsec or so, velocity differential is about 1 kilometre a second, end to end. So, as we know from Prof, we've got a parsec in 10 to the 6 years is 1 kilometre a second. So, a million years later, these things may collide and combine as they do in the simulations, but of course we don't know what the vectors are in 3D, so in fact they may not. In a way, that was sort of what I was saying before, that you form little entities, and depending on the larger scale kinematics, they might get together and form a cluster, or they might just go off as dispersed things. So, my question, if he was in the room, is what is the problem with this data in relation to the sort of things that are coming out of the simulations? It actually seems, to me, to my mind, incredibly consistent.
So Kathy,
Yeah,
I'll
yes.
comment on his behalf if I
Yes,
can,
yes.
and I may misrepresent him,
Yeah.
so let me just speak for
Yeah.
myself. That core, say the one with all the little red guys,
Yeah.
could that be, is there more in CO? I don't know what mass comparison you did to say that it's half and half. Do you think
Yeah.
you got a good CO mass estimate of that?
He said that the common density of each individual core was about twice the common density of what else is along the line of sight.
In the ammonia?
No,
Or-
it's not.
So,
it's not ammonia as well.
It's, well, or whatever
yeah.
that.
Yes.
I'm just wondering if
Yeah.
there's a difference in the total mass in low density tracers versus this high density tracer. And if your fractional mass is the total mass of that cloud, and if the velocity dispersion of the intercore medium is still 1 to 2 kilometers per second.
Yeah, I'm not sure if I'm quite getting your point, because even if some of the mass that I thought was, maybe you're not making this point, if we just look at the potential created by these cores, which are as masses we do know down there, and ask free fall time down there, it's 10 to 5 years.
I guess I'm wondering what the total virial mass is of the whole thing, if it's 10 times more than the mass that's in these dense cores. It's a little bigger scale, but it's not that much bigger scale. And I'm wondering what the velocity dispersion of most of the mass of gas is.
He's asking if the cores are embedded in a larger massive cloud. Not the whole system, but just that clump.
Let's call it a clump.
Okay,
Like if 90% of the mass
Yes,
in that
yes,
0.1
yes,
parsec is in
yes.
CO, moving at 1 to 2 kilometers per second, creating a potential on the whole, which is 10 solar masses instead of the sum of those 8 cores, which
okay.
might be
I
2
get
solar
what-
masses.
Yes, I think I'm getting it. I think I can see what you're saying. That's not discussed there, but that is discussed in the Kirk paper that you pointed me at. So, since I'm almost out of time,
Sorry,
I should probably
we should talk about it in a
continue, but
second.
I'm finding this very interesting. Yes, yeah.
Tell us later about the I didn't get it.
Yeah, exactly. But also the other thing is that he concluded that these clumps were moving relative to each other. So I call them clumps, these various little islands of points here. But what he did is he said there's a global gradient across there, and I'll subtract that out. And then when I subtracted out the global biggest shift, what I'm left with is very small. And to me, I can't see how that implies that the things aren't moving relative to one another. I mean, if you've seen something that's moving 1 kilometre a second faster here than here, I don't see why you should subtract that out if you're asking, should these things be moving significantly over 10 to the 6 years? So again, there's a conversation to be had with Philippe there. There's other studies extremely interesting as well. So this is on Perseus. This is Kirkett out of Goodman's group. And well, you can read it for yourself there. They've got velocity dispersions among the cores of 0.2 to 0.6 kilometres per second in 1D, so really quite similar to what we saw in Ophiuchus. And it's about half the velocity dispersion in the 13 CO that you see along each line of sight. And there's an interesting paper here, I like it very much. It's a letter by Offner et al., where they do a simulation now, and then they observe the sync particles that they create in their simulations and look at their velocity dispersions compared with the gas from which they form. And the results they get in terms of the ratio of the velocity dispersion of the cores, both to the sound speed and to the velocity dispersion of the 13 CO is the fluff. Okay. It's actually very comparable to this. And actually a number of things in this paper that I don't understand. I think it's probably because it's a letter, so it's very compressed and there's not quite enough information to make sense of it. But as far as I know, it's the only simulation at the moment that's really taking on this question about the differential behaviour of the dense gas, the fluffy gas, and the cores. Now, I think everybody, when they look at observational data, has a prejudice, and my prejudice and Philippe's prejudice is different, so we see different things, and that obviously applies to both of us. So let me just tell you what I see, or rather it was Thomas who saw this and pointed it out to me, what people from the dynamical schools see when they look at this beautiful Herschel data. So this is the exploding sausage simulation, if you like. This is a lovely map of Aquila showing the filaments in there, and we've got here the economists and our work. This is the distributions of dense cores. They are still in the filaments in general, but down here is the cluster, and the stars in there are in the protostellar phase, so they're more evolved. So to me, looking at it from my perspective, this looks like what we see in the simulations, that things condense out of the cores and then drift in and feed the cluster at the centre. But as I say, that's theorists' glasses view. So I think it's a very, very interesting area, and the data is there, we can always come.